Hello, it's Rasmus Benestad, and I am going to talk about analysis with smart data. Basically how to make use of the data structure and the metadata to make the analysis much more efficient and simpler. So I am going to start with an example. So here we see an animation of the global warming simulated by a global climate model. And this animation was made only with a few lines of code, which I'm going to show you. So the code was able to fit within this page here. So basically, to make this animation, I first needed an R package called ESD and an R package called animation. So I loaded these libraries in the R console. Then I needed a function called frame here, which maps the temperatures on the sphere for different years and also at different angles. Then I needed the data itself, so I downloaded data from the KNMI Climate Explorer and I saved it locally on my disk as a file called tas.nc. It's a netCDF file. And then I needed to read the data into the memory, so then I used the function called retrieve from the ESD package. And also I wanted to plot the annual temperatures, annual mean temperatures, so then I took the annual of that. And in addition, I wanted to just plot the anomalies rather than the full data, so then I took the anomalies with respect to the 1961 to 1990 baseline. And to do this animation, I also needed to know how many years I had. So n is the length of the record. And then I use the save GIF function from the animation and loop over the number of time steps. And for each time step, I call the function frame to plot the temperatures on the sphere. And that's it. But there's so much more behind this, because I couldn't do this without you making use of data structure and metadata, because the computer needs to know exactly all the details how to do the plotting and do all the work. And the truth is that a lot of information is stored in this variable called tas. So if we look at its structure, and we can use this this command in R called str, which reveals its structure, and it gives you information about what it contains. And it contains much more than just the data. It also contains information about how to work with it. So it's a zoo object, that's a time series object, which has dates from 1861 to 2100, and it's stored in the data is stored in two dimensions. One is time and the other is space. And then there is information about what kind of variable it is and what units there are and dimensions and so on. And also there's like some information about this history, how like what's behind this data. So basically it will say that it was read in with the this function here. So, and when I talk about data and structure and metadata, I want to distinguish between data stored in files on a disk and data stored in the computer memory, or I will refer to those as objects. So and when it comes to the files, a lot of work has already been done when it comes to how to store the data and the metadata together. I'll come back to that in a second. But there has been less sort of considerations on the data objects, how to represent the data and all information in the computer memory while you actually do the analysis. But what we know is that a common file structure has been hugely beneficial, so that makes it much more easier to collaborate and also use the same tools. And this is also true for the standard object structures in memory as well. So we talk about two things. One is the class, and that basically this is in the R environment. That provides information about what kind of structure you have. So and you can see here as an example for the task that we looked at, it's a field object, but we also have monthly mean data. That was before I took the annual mean of it. And also it's a zoo object, which means it's a time series object. And then we have the attributes, which are on top of that. And the attributes contain the metadata. And the question then is, what type of information should be included and how should it be organized? And here is one example. I just show the names of the attributes of TAS here. And we see it has dimensions and index, and it has class and variable and long name units and so on. And the number of attributes could be a long list, or it could be like a small set. But the idea here is to have like a standard set so that they look the same, and you can make use of tools that will look for the same types of attributes and make use of those when you do the analysis. So the benefits for having the structure and also the attributes, so the metadata, is to simplify and let the code do the housekeeping, as I showed in the first example, and that makes the analysis quicker and more efficient, at least to do it, to set it up and test it, even though it may run a bit more slowly once you run it, but if you just run it once, it doesn't really matter so much. So the R-based ESD tool uses something called S3 programming style, that uses the object class to define what kind of type it is. For instance, we used map here, and we had a field object, so we'll map the field in a different way than mapping, say, a station object. Or you can use plot or subset or summary, and you don't have to specify what type, because the S3 programming technique takes care of that. And also in these functions, the attributes will also be used in order to show the right, say, the legends or so on. And also the metadata or the attributes are very useful for searching, sorting and extracting information from the data objects, especially if you have many stationed records in one station object. You can sort of subtract, you can subset and take out what you need. And in addition, by adding like a history stamp, Daukanal also provides an increased transparency and provenance and replicability for this analysis as well. Aiming for is to have a set of standard conventions, which makes it easier to collaborate and also use the same tools. So one example is the netCDF CF convention for the file types when the data is stored on disk. And this is mainly true for the field type of objects, but there are also other types of objects which we don't really have any conventions for. And the benefit of that is also that you have some kind of quality control, because these conventions and also the code for reading and analyzing these have been tested and verified many times and by a diverse set of users and in the diverse use, and by having many people using the same tools, you tend to unearth bugs and also weaknesses if there are any. So the different data objects here, we have the field objects, which we have already seen, like the simulation of the global warming. And that's the field object covers longitude, latitude and time, and sometimes also like the vertical coordinate is set here. It's stored in regular grids, and we can make this actually follow the CF convention also in memory. And then we have a station object, and then the station has longitude and latitude, or we can have many stations as well in one object, and also time. And the longitudes and latitudes are not regular, so the coordinates are irregular. And then we have the event type, and maybe even like say radiosondes. In addition to these observations, we also have derived objects like storm tracks. So then you have longitude, latitude, but also the identification of the storm track itself, the ID number and time. Or you have the intensity, duration, frequency curves, IDFs, with longitude, latitude, and time, and then we have the time scale and also the return period or probabilities. So we have the longitude and latitude and maybe a threshold value. There are also the empirical orthogonal functions, EOFs, which has longitude, latitude, and also the pattern index, and also the time matrix, the principal components, which are pattern index and time. We have principal component analysis, which are a bit similar to EOFs, or even results, like say downscaled results, which also have information about the methods itself. So here's one example of the station object. So we read data from Oslo here with station ID from a thread server, and then we can just write summary of Oslo, and you get like the minimum and maximum data for each month, and also the mean and median. And you can only get these kind of results because the Oslo object has information about the months and so on. And contains more information, than just the data, because it has the metadata. And we can also look at, say, like a group of stations. So here we read like stations, the temperature, 2 meter temperature within this region from the same thread server. And you see we have, when we look at the dimension of this object, we have 7,400 days, more or less, and 138 stations. And now we can actually say, okay, we want to make a map of the maximum values for these stations, and we just do it with this simple a command, and then we get the map here. And we can only do that with like a good data structure and also the appropriate metadata as well. Here is another example of a data type. So this is the event type. So I'm showing you how to actually derive an event type. So basically we start with the sea level pressure from era 5 reanalysis, and then we apply a method we call CCI, which is calculus-based cyclone identification for this data. And then afterwards we and that would give us the location of local minima in the sea level pressure for the different time steps, and then we can track this to make a storm track. And then we can make a map of the track here, and this is the map of the track here. And you can see that this is a storm. This is a Hurricane Matthew. And if we look at the class of this object, it's an events class, but also it belongs to the data frame. And the names of the attributes, you can see it has variable, long name, calendar, and so on. But since this is a data frame, it contains more, the data itself contains more than one type. So if you look at the names of the sea tracks, we see it contains date, time, longitude, latitude, pressure, the center, maximum gradient width, and so on. Or the motivation for this ESD package, which makes use of all the data structures and also the attributes, was AGO. So basically you get an output from some operation, like a function, and that can be the input for the next operation or a function. So you can build up like a more complicated analysis by adding small bricks of simple analysis. And in the same way as you build on previous step in the analysis, it's the same way as you build like a more complicated structure with Lego. So, and you can only do that if you have like standard structure, and also like you have organized the metadata in a standardized way. So you use a standard convention for that. So I want to show you one example here how this works. So this is I read it at the air surface temperature, just like a small set, like small region here, and then I say, okay, I want to estimate the empirical orthogonal functions, the EOFs, and I can do that. but also it is possible to do the reverse, to actually use the UFs to reconstruct the original data. So then I do that. So I say, okay, I want to reconstruct the original data from the UFs, and then I wanted to look at the difference between the two. But in order to do that, I also needed to copy all the attributes of the original data. So then in order for my function to work, and then I use the command map, but I get an error. So then I want to say, okay, why do I get the error for that? And the reason is that the class is not the right. So the class changed when I subtracted this, but the attributes were okay. So if I change the class back to the original type and then write map, then I get the map. So this is the map, and you can see it looks very noisy, but that is because the values are really small. So there's hardly any difference between the original data and the reconstructed data. So it shows that it works. But you need to have the correct structure as well as a set of metadata, or the convention. So the metadata could be more than just information about the data. You could also actually include code as part of the metadata to tell the computer how to deal with it, either how to organize it, or how to read it, or how to do some kind of operation on it. And we do that as a part of a history provenance thing in the ESD package. Every time you do an operation on data, it will add to a list of lines of history to show what has actually been done with the data to that point. And of course, it's the metadata is important for searching, sorting, and filtering, but also to assist analysis. So you can maybe use some of that metadata in some kind of regression analysis or some kind of classification. So what I really want is to have some more discussions about general principles. And I think one important thing that everybody should have in their mind is that they should think that others will use your data, and to make it easier for them to use the data. Because if you try to write new code every time, there's a bigger chance that there will be a bug there, or you'll do something wrong and get some misleading results. But by using data with standard structure and conventions, you can use the same types of tools, and which have been tried and tested, and now can spare you from making unnecessary mistakes. And also, I would like to say that divided files are annoying. So typically in the past you had one file with data and one with metadata, and then you had to read both of them in order to get the whole picture. And the grep format used to be like that, and I have had some mixed experience with grep files, but also shape files, because often the metadata tends to get separated and gets lost along the road. So it's much better to have them all stored together. And then the idea is to basically inject the data straight, and the metadata straight into the memory. So when you read it, you read everything that you need. And typically this is what we do with the netCDF and also the RDF files. You read like a more complicated structure than just the numbers. So thank you.